About that. So my work is mainly based at Foster & Partners, but besides that I also teach a little bit at the Bartlett, and I'm also one of the directors of Smart Geometry. But what I'm going to talk about today is mainly based on the work from Foster & Partners. So, now, this is the little team that I co-head at the moment. It's called the Specialist Modeling Group. It's exactly where we sit in the office. Now, this team has been around for about 18 years now, and Juve started up the team around, I think it was 1998, I think, or 97, and it was around the time that we started to design rather complex buildings, mainly geometrical, like the Swiss Re, the Gherkin, or the Stage, the Gateshead. It was also around the time of the British Museum roof. And although we wanted to design these things, we feel that we didn't really have the tools to design them and also to fabricate them. So Yachtplus went out, and there's a little bit of history which might be quite interesting, went out to kind of look at some consultancy. So we had Decoy and Mark Goldthorpe helping us out, doing some models, and we also had, you know very well, Mark Burry at RMIT starting some parametric models for us. But we figured out really quickly that we really wanted to have that technology and that capability in-house, because it's much quicker to actually, because it's part of the design process, right? It's not part of the building process, part of the design process, so you want to have it in-house. And that's why the team was then started by Hugh Whitehead, around 1998, I think. Now, the beginning years, this is kind of what was on most of our screens. I'm just going to see if the videos work. Yeah, they do work. Hooray. So there wasn't any Grasshopper, there wasn't any generative components, there was barely scripting languages available. So these were a few tools that we've built ourselves. A lot of them are profile driven, that are then somehow in 3D are put together. A lot of kind of hot wiring behind the scenes happening here within the software. So these was kind of like what I think of it as the beginning years of the Specialist Modeling Group. And this is kind of the project that came out of it. GLA, Joseph Ventura, Gateshead, Swiss Re. Now, although the team really started by mainly looking at geometry and how to fabricate this complex geometry, we quickly understood that besides geometry, there's also the building physics, that these buildings behave differently, and that we can actually start designing with the behavior of these buildings. So, for example, Swiss Re has a certain airflow around it for the natural ventilation. You know, you're going to use these principles, the building physics principles, to drive your geometry, and they're in constant dialogue. Now, the team has grown, right? And this is kind of a bit of an overview of what the team looks like now. I've got myself and Irene heading the team with, I look more after geometry and fabrication, and then on the other side, Irene looking at building physics, anything to do with airflow, thermal analysis, wind flow analysis, and so forth. Now, so this is a kind of a typical project. This is the National Bank of Kuwait that is currently under construction, and you quickly start to understand what our team is involved in. We are kind of an internal consultancy for the architects and the engineers. So we always come in when things get a bit difficult or things get quite digital. So as you see, what we're doing here is looking at acoustics analysis, wind flow analysis, looking at optimization for geometry, for fabrication, thermal analysis here, and looking at constructability. So this is the typical project. We kind of help out, although it's not our core thing, we do help out with kind of what we call advanced BIM. So not the normal BIM sites, but if things get a bit complex, we might help out the teams on that as well. So, and this is the project now under construction. Now, the team exists out of, I think it's 23 now. There's a bit of an old slide, there's a few people extra and a couple of people left as well. But if you look at the team, and I'm not sure if you can read it, or maybe just a little bit, the team really started out as architects, but it's grown much wider. So now we have architects, engineers, structural engineers, mechanical engineers, but we also have material scientists, we have a mathematician, an artist, two acousticians, people with an aerospace background or computer science background. So it's a very much interdisciplinary group, the team. But one thing really, well, there's actually two things that really kind of combines them, is that besides being experts in their own fields, like the acoustician is, of course, a perfect acoustician, they're also digital experts. So, for example, Arthur, the team, and Phil, they wrote their own software, their own acoustic software, before they came to the team. So, and besides being experts, they're also still designers. I think that's a very, very important thing. So they're not just, we're not hiring computer scientists or pure computer scientists. We're hiring computer scientists that somehow has an affinity with design or is still a designer as well. I think that is one red thread that kind of runs through the team, and that is really important. So I spoke about that. I'm going to have a very quick slides to show you a bit of an idea of what the projects is that we're involved with, and then I'm going to go talk a bit more about the Moon and the Mars projects and the 3D printing. This is Crossroad project, a new station in London that we're looking at. Very much digital fabrication again, where we're looking here at every single node connection of this project. Although it looks very irregular, it actually isn't. Every node connection is just slightly off. And this is the reason for that is that we want to have the die grid that you see here, these lines, to in the end line up perfectly with our the end overhang. Other projects that, again, quite a bit of digital fabrication involved is Kuwait Airport, which is a concrete roof over the airport built out of prefabricated elements that you see here being brought on site. It's built out of columns, beams, and then shelves. And we helped out the fabrication process quite into a bit of detail, which actually normally doesn't happen on architect projects that much. We went all the way into defining each of the cutting planes of the formwork for the concrete shells. So going into quite a lot of detail of these projects. And then to kind of bring ourselves a little bit into space, I always like to show this project, which is our spaceport. It's not an airport, it's the world's first spaceport in Nevada, and this is the place where hopefully soon the first Virgin Galactic flights from Richard Branson will take off. So, brought us a little bit closer to space now. So let me talk a little bit about our 3D printing Moon project. Now, a few years ago, we were aware of a call of the European Space Agency that they wanted to look into what you could do with regolith. And regolith is moon dust. Right? Could you use that material as construction material from the moon? Could you 3D print with it? So that was the actual brief from ESA. And this is our project brief. You know, look at what we could do with 3D printing regolith. Could it be protection shields and so forth? And what would that look like? Now, for that project, because it's a very technical project, we wanted to kind of set up a little consortium. So we start working with a few different companies, and I think that's always quite interesting. If you go into a field that's really technical, you have to have some experts there that help you along the way. So the first company that we got on board was Alta. Alta is a space engineering firm in Italy. They mainly look at propulsion systems, but of course also experts in planetary science. And so they brought in a lot of the data into the project. And also did some testing in their vacuum chambers, which you'll see later. So we also worked with Enrico Dini, who we were going to use in his 3D printing process. So he has a really large printer for quite a few years now, near Pisa. And it was this chemical process that we're proposing for the moon as well. When you suddenly have a completely different environment, you have to design something in. So what you're going to do, you're going to start to look at what was there before. So what was the precedents? Now on the moon you don't have that many precedents. There were the Apollo missions mainly, and this is not really a base. This is not really a moon base, because this is what I call a very expensive camping trip. Because the largest Apollo mission was only 3 days. So looking at habitation on the moon, looking at a base there, this might look very different. So we also looked at existing research. So what kind of moon bases have people proposed before us? And what we found out that the research really fell into kind of 2 areas. Like one area was very much hardcore science, white papers, talking about a very particular aspect of designing something for the moon. It might be an airlock or something like that. And on the other hand, you had the artist impressions, which was quite fluffy and not really like this one here, not really based on hard science. So what we wanted to do is somehow stay in the middle and have a way to be based in science and make a proposal that really makes sense. But on the other hand, also not lose track of what this whole idea could be, what it might look like. Technologies that are out there. So what is long-term space habitation that is out there now? Well, the only real example is the International Space Station. Right? It's out there for quite a few years, and when you look at it, you see the geometry of it is mainly an assembly of cylindrical elements. Right? And there's a very good reason for that. So this is just kind of tubes all connected to that, because that is really the maximum volume that you can get in Ariane rockets, for example. So it's just the maximum volume that you get on a rocket. So these elements then combine together.
So cylindrical elements, like you have here. This is the Columbus module. This is the science station on the International Space Station. So, like I said, the maximum volume that you can get in the rockets. So, but then when you look in the International Space Station, what does it look on the inside? Like a real mess, right? It's mainly corridors with lots of laptops on Velcro. So this is not really a space that we want to stay in for a year or longer. So we start to think about it. How can we actually get better spaces out of this, with the restriction of having, fitted in a rocket as well? Now, the other restriction, of course, is weight. Right? To get anything to the moon, any kilogram of material to the moon is going to cost you about $200,000. So it's very expensive. Because gravity is very difficult to escape. So what do? We started to look at, and this is just a kind of an inspirational image, looking at inflatables. This is a Thomas Saraceno observatory. So inflatables are interesting because what you can do, you can actually start compacting space. Right? Compact it, it fits top of the rocket much smaller, and it's super light. So yes, this is quite a good idea, we thought. Of course, you're never the first one to think of a good idea. This is a company called Bigelow. They're looking at commercializing space stations and doing that with inflatables. This is a technology that's actually been developed by NASA over 10 years' time, and is now probably going to be put into commercial use. Well, they already have actually an inflatable satellite. This is the Genesis module. And they're looking now, and I think it might have just happened, is they're flying an inflatable element to the International Space Station and will inflate it. That will be kind of the first inflated module in space. So, looking at our habitat here, this was our proposal. You can see there's a few elements that we kind of borrowed. First of all, there's still this cylindrical element, which is very similar to what you have in the International Space Station. It's a hard shell element. All the life support systems will be in there, and we're also using that as an airlock to go to outside. Out of that, we have an inflatable. Now, of course, that inflatable needs to be protected, because Moon is a very harsh environment, and you see this kind of shell structure above it will protect it. And this is a 3D printed structure made from regolith, from moon dust. Now, like I said, Moon is a really harsh environment. Let's look at the parameters. Let's look at the environmental parameters of designing on the Moon. First of all, radiation. Radiation comes from this cosmic radiation, is also solar radiation. It's the solar radiation which is really the most damaging. Definitely when you have solar flares. Now, to protect yourself from the sun, right, is that what you have to do, from the radiation from the sun on the Moon, how do you do that? Well, first of all, we need to know where the sun is, right, to protect ourselves from it. Knowing where the sun is, we're going to need to know where we're going to be on the Moon. So we looked at a couple of places, but one of the places could be near the equator, where the Apollo missions landed. Now, imagining standing on the Moon, on that place, what would happen in the daytime, in a day on the Moon? What would happen is that you will see the sun coming up, and it would take 14 days for the sun to rise and go down. Then it would be night for 14 days. Not a great location to be, right? If you have pitch darkness over 14 days, and it will get really, really cold as well, because you have the nighttime for 14 days. So we looked at location on the South Pole, mainly called the Shackleton Crater, which is right here. What would happen if you were standing there is, the spot right there, is that you will see the sun being on the horizon, and it will go around you over 28 days. Right? So it would always daytime, well, almost daytime each time. And you kind of see what is also interesting is that looking at this crater is, by the way, this distance from here to here is about 50 kilometers, and the crater is 4 kilometers deep. So this is a huge crater. There's some coloration on here. So what we analyzed is that the top side of the crater, where it's red, that indicates where we have eternal daylight. So there's always daylight in that spot. Now, because the sun is really on the horizon, that means that if you're in the crater, you actually have continuous nighttime, right? So, and this is also the places where we expect to be ice, so, and water. So it's an interesting location to be. So we know where the sun is going to be. It's going to be always on the horizon, so we know how to protect ourselves from that sun. Another environmental factor is meteorite impacts. Now, of course, what happens this is the surface of the Moon. What happens on Earth is that meteorites mostly get burned up by the atmosphere. There's no atmosphere on the Moon, so every crater is impacting, every meteorite will impact the surface. And it's kind of scattered with large and smaller craters. Now, to put it in perspective, if you a bullet will normally go roughly at around the speed of a kilometer a second. Looking at meteorite impacts, that will be about 18 kilometers a second. So, it's going to hurt. It's going to have some impact. And these are not really massive rocks that we think about. These are actually micrometeorites that would impact our surface. Third one is extreme temperatures. Now, we always think we work all over the world. This is our Mazda project near Abu Dhabi, where we used to work in really, really hot climates, so plus 50 degrees. Or here's a project in Kazakhstan, minus 35. So we thought, well, we kind of lined up to deal with extreme temperatures. Of course, on the Moon, it goes quite different. You can go up to like 100 degrees to minus 160. So having some mass around you, some thermal mass, is really going to help you regulate the temperature inside. So, taking all these parameters, right, the radiation, meteorite impact, temperature, how would that define that shell structure? So, design, we said we have an inflatable structure. We want to create an offset from that. So we don't want to build our dome structure directly against it, because the regolith will be very tough material, very coarse material, so we wanted to kind of stay away from it. So we're creating a kind of a vacuum in between it, which is about 300 mil. Then we said we're going to print with regolith, with moon dust. The quality of that material will be even that solidified material will be very poor. So we're thinking to really only work in compression. So for that we use catenary structures. So that is our first line here, going over our dome structure. Then we know, well, we need to protect ourselves from the sun, from the radiation. We only need to do it in a horizontal fashion. The radiation will only hit us horizontally. So whatever mass we use to protect her with is going to be horizontally offset. This is about 1.5 meters. So these numbers we got by working very closely with our space engineering firm. So they came up with these numbers through a lot of research into and white papers that happened within that field over the years. And then looking at the meteorites can impact us from any direction. We probably need around 800 millimeters of protection there. So putting all these together, you get a really defined shape of what that shell is. So this is kind of a bit of an overview. You get the hard shell elements and our inflatable, in which we install all the labs and the living spaces. And around it, we have a 3D printed structure. Now, as we said, we're going to use local materials because it is much cheaper to use whatever is around you, and instead of bringing it from Earth. Now, the process that we're using to do the binding was using magnesium oxide and a liquid. So we still had to potentially bring certain parts of that binder to the moon. So what we wanted to do is somehow minimize that still. So you can see here one of our printers. Oh yeah, one of the interesting things to mention also is that, of course, you're not going to bring a big printer to print something that is smaller than itself. What we wanted to do is have a much more smaller printer, right? And this is what kind of our first initial idea. This is only a sketch in a way of what that printer could be. You could scoop up regolith and then print it layer by layer. So this is a little stop motion almost of 3D prints, showing how it could happen. You can have a hard shell element. Out of that you can get an inflatable structure. That is really the scaffolding for the printing process. You can see there little robots printing bit by bit the whole shell. Now, of course, that shell structure was completely solid in the earlier renderings. We wanted to start looking at, is there a way to minimize the amount of binder that we use? And of course, when we start doing this, you start having these, you want to have a structure in there within the inner and the outer shell. And you, as an architect, you start thinking of the geometries and the topologies that you're used to. So we start to design something like this, but because this is what you have in your head, right, through education. But what we really need to do was looking more at natural processes, because with 3D printing now, any geometry is possible. So why not look at natural structures? So in the end, we kind of decided on using a closed foam cell structure for this, so that only the cell walls would be printed, and inside you would have loose regoliths. For a few reasons. This is a mock-up being printed at Enrico Dini's facility. It's about 1.5 tons, about 1.5 meters by a meter size part, and that is printed with moon dust simulant, so regolith simulant. It's not really moon dust because that'd be very expensive, but it is. It has a constitution of moon dust, and it's mainly volcanic ash material. Now, what you see, once you print this process, when you do layer by layer, with a closed foam cell structure, you have each layer that you print is almost a stable structure. Right? So that's one of the reasons why we use the closed foam cell structure. Another reason is because you get a hard material, a soft material, which is really good for meteorite impacts. So a meteorite will impact two different types of material, hard, soft, hard, soft. So it's a bit like a bulletproof jacket, you have also different materials, different layers, dissipate the energy much better. So this was then the kind of the massive block that was printed. Of course, this was all scaled up to Earth gravity. The moon has 1/6 of the Earth gravity, so the real part is much thinner. Now, okay, we were quite keen on testing out the printing process, but what we really wanted to do is see, well, does this work on the moon, right? One of the factors that will influence that process is the fact there is a vacuum. There's no atmosphere. So we're using a liquid binder still. So would the liquid binder not just completely evaporate the second you start printing? So for that, we want to do a proper simulation. So we set up in Alta's factory, we set up a very small printing process that was printing a tiny little blob in a vacuum chamber. It took about 3 days to get the vacuum, and this is the little test case. What also is happening here that we're not printing on the top layer. What we're doing is we're injecting the regolith and then printing about 2 centimeters underneath the surface, which then, stops the evaporation happening so quickly, and the chemical process we were hoping was going to happen before the liquid evaporates. And hooray, that was the first 3D print happening in a vacuum. It's a tiny little ball. But it really showed the process. And it was very important for us to really go and do these kind of tests, these scientific tests, to see, is this really a feasible system or not? I'll skip through these a little bit because I want to kind of show a little video first. So this video actually kind of shows you, this is a video that we made about a year after we finished the project to really kind of go out to the press and show the project a bit more in detail. So let me just play that now.
Planet Earth is protected by the atmosphere, the layer of air and gas that surrounds it. The atmosphere shields the Earth from solar radiation. It keeps the temperatures balanced, and it protects us from meteoroids. The site of our lunar base is the Moon's south pole. Conditions on the Moon are very different from those on Earth. Because the Moon has no atmosphere, there is no protection from solar radiation. The temperature fluctuates. And there is no protection from meteoroids. The lunar lander has detached from the rocket launch and is on a course to Shackleton's Crater, the Moon's south pole. Attached to the lander is a cylinder which contains an inflatable dome and 2 robot 3D printers. After the cylinder containing the habitation capsule has been unloaded, a dome is inflated from one end. This provides the support structure for construction, a little like scaffolding is used to build on Earth. The Lunar Habitation is built by a series of robot-operated 3D printers. At one end, it has a scoop to collect the regolith. In the centre are the containers for the printing material. At the other end, there is a robotic arm with a printing head. The robot collects regolith from the Moon's surface. Layers of this moon dust are built up over the dome to create the protective shell. This process takes about 3 Earth months. The shell is made up of a hollow, closed cellular structure. Under a microscope, it would look very similar to the structure inside a bird's bone. Like a bone, it is light and incredibly strong at the same time. When the lunar base is complete, it can house 4 people. Inside the dome, they're protected from solar radiation, meteorites, gamma radiation, and high temperature fluctuations. The original capsule functions as an airlock and technical support module. The skylights draw daylight into the living and workspaces, which are sheltered within a pressurized enclosure. This method is a pioneering advance in space-age construction. At Foster & Partners, we're used to designing for some of the world's most extreme climates. We often use materials found locally to create sustainable buildings on Earth. While the Moon is an exciting new territory for architecture, the value of this logic endures.
So that was the Moon project, and you might think, this is kind of a once-in-a-lifetime project you can do. Well, funny enough, about a few months ago, that became like a twice-in-a-lifetime opportunity when we joined a competition to design Mars base habitat. So it was really interesting because for once we really had experience of designing something in space. And so this was a competition set up by NASA and America Makes. And it's still ongoing, so we came second in the first phase. There's a second and a third phase as well. And so let me just take you through that. So this is the Mars base project. I just want to give you a quick slide of what it looks like. It looks maybe quite similar to Moon base, but actually quite a lot of differences. First of all, Mars. Right. So what is the main difference between Moon and Mars? Well, first of all, it is really, really far, and that has a lot of consequences. Think about it. So this is the kind of images that you often see of what our solar system looks like, and they really annoy me sometimes because they're really inaccurate and they really don't show what the magnitude of the solar system is. First of all, the scale is wrong of the planets. They're probably a little bit more like this, and what you really want to look like is what the distances are, because here the distances are completely off, of course. So think about it like this. So we think the International Space Station is far in space somewhere. Well, it only sits about 400 kilometers above the surface. It sits at lower Earth orbit. If you then go to the Moon is about 385,000 kilometers away. So it's about 1,000 times the distance from the International Space Station to the surface of the Earth. And even this image I always find very not, well, of course the correct image, but it's, if you look at the real distance, so this is the Earth and this is the Moon. That's the actual distance between them. And so the distance then to Mars is again 1,000 times that. So we're talking about at the furthest away, because the distance between Mars and Earth, of course, varies. It varies between 50 million and 400 million kilometers, right? And this is what you see here. That little bright dot is Earth seen from Mars. Now, the distance. This is huge. How to get there? Now, these are actually two ways to get to Mars. One is having a rather long way there. You stay there for a very limited time, for about 30 days, and then another long way back. In total, more than 3 years. Another way to do it is that you go a much shorter way, and depends where the Earth and Mars are at that moment, and then you stay for a 500-day period. For what is it? Yeah, it is 500 days. You stay for 500 days. Again, the journey will be in total just over 3 years. So we chose the long stay mission, of course. A very thin atmosphere. So it's the Moon, you don't have an atmosphere. On Mars you do. It's mainly CO2, and it's 100 times thinner than the Earth atmosphere. So what is the consequences of that? Well, most of you have seen The Martian, I hope. The opening scene where the astronauts get blown away by the storm on Mars is, although The Martian is actually quite accurate scientifically, that scene is completely inaccurate. Because although if you could have like 100 kilometers or 200 kilometers storm on Mars, which happens, but the effect of it would almost be nothing. because it would be 100 times less wind pressure than on Earth. So you actually have less particles actually blowing against you. So, okay, there is storms on Mars, but they actually don't have that much influence on you. What does have an influence is that the Mars atmosphere is much thinner. So you have less resistance, which will have an effect on landing. You know, the way we land on Earth is like if a space module runs back on Earth, it uses the atmosphere, the resistance from the atmosphere, to actually lose speed, to slow down. That happens less on Mars. So which is a bit of an issue. It's cold, right? It loses heat quite quickly. Mars. It's also further away from the sun than Earth. And this is the temperatures that we deal with, -20 to -125. So it's cold, but it's actually much more manageable than the temperatures that you find on the moon. And radiation. Again, we need to protect ourselves from radiation. Why is that? Well, mainly because Mars doesn't have a magnetic sphere, magnetosphere. You know, Earth has a magnetic sphere around it, so the radiation particles that get deflected. On Mars, that doesn't happen. So, same thing as on the Moon, we'll need to protect ourselves from that radiation again. It is an interesting thing. It's also about the radiation that you're going to get on the way there. So we chose for a mission of having a very short period of time spent actually traveling there and a short period back, because we want to minimize the amount of radiation that you get traveling there. They're also thinking of actually sending older astronauts. So astronauts are actually getting quite older at the moment. They're not that young anymore. Astronauts are, I think the average age is around 40, I think. And one of the reasons is because they're going to get radiation, and the chance of getting high developed cancers is less if you're older. It's just the fact that you are older, right? So the reasons, that's actually one of the reasons that we were thinking of sending older people, older astronauts to Mars. Then, what material do we have? Well, we have a little bit more than on the Moon. We have mainly CO2, which kind of which could be used a lot to fabricate, for example, oxygen, you know, and the regolith we have as well. So this is a kind of, I'm not going to go into this, this is actually a kind of an interesting graph showing what you need to do to go from pure regolith and CO2, what you chemically could actually make with it. And you actually kind of, this is a more and more complex way to do things. But the first thing that you can do is really using regolith and melting it together. Right, so that is one of the first ways to really make something, a material, purely with regolith. The missions are also really high risk. If you look at the Mars exploration, you see there's lots of failures here. So the bottom one are all these short little stripes of failures, and there's a lander and a rover are the ones that are longer. So actually a lot of missions failed to Mars. Now why is that? There's a few reasons for that. So this is a mission, of course, successful, is the Curiosity rover. The fact is, you know, the distance is so far that there is no direct communication between Earth and Mars, or any rover on Mars. So it takes about 20 minutes for a radio signal to get there. So imagine actually kind of operating the Curiosity rover. You can't do it directly. You can't sit there and go left. Well, you can tell it to go left. It takes 20 minutes before Curiosity knows it needs to go left, and it will take another 20 minutes before it tells you that it went left, or it didn't go left, or something wrong happened. So all these things we want to kind of take in consideration on when we designed the Mars habitat. So one of the things that we thought about, you know, if you look at Curiosity rover, it's a highly complex machine, right? It has a lot of backup systems, a backup battery for the backup battery of the backup battery, has 6 wheels, it can lose one can get jammed, it can lift it up, the other one can keep on going. So what we thought, well, maybe there's another system, right? And we kind of compared to like the Hubble telescope. Again, one machine that is extremely complex. We want to take more of a bit more of a contemporary approach, where we look at CubeSats. Now, CubeSats are satellites that are about 10 by 10 centimeters. They're very simple machines, but somehow, if you have quite a few of them, they can do the same tasks as larger satellites. Now, the great thing is about a CubeSat, they're much cheaper to launch. And if one fails, that's fine. You might have a few other ones left. So we wanted to start looking at can we define a resilient system for Mars as well, definitely for the printing process. So this was a team, it's called Team Gamma. We actually worked with a few other companies together. One was called Astrobotic, which was a moon rover company. They design moon rovers. And the other one was, well, not a company, it was Penny Boston, which was a planetary scientist from New Mexico University. So if you design something for Mars, first thing you need to do, which was something you don't really always think about when you're designing for anywhere else on Earth, for example, is how to get the materials there. So here's one of the ways to do it. So whatever module you bring to Mars, you enter with an aeroshell. It's a shell, it's a shield that will get burned up in the atmosphere. Second, what we have is, I was going to do it again, isn't it? Is a supersonic parachute, a band parachute that will open up when it is still in Mach 3 or something. It will open up and start slowing down the module. And the third one is then a subsonic parachute to kind of bring the module down. Now, if you see here, you've got these, I'm not sure if you see it, but the module exists that you bring down. This module could be anything, right? The module you can see here has all spheres around it. Well, these are a massive airbag, you know, so you don't land it really softly. You start dropping it from a few meters, and it just bounces around, right, until it lands, until it stops. Now, what we thought of then is, well, you want to get your modules all together. If you have different modules coming together, how are they going to travel, right? So one of the ideas was that to use the airbags and inflate them and deflate them, you can kind of just about see that here, is to start rolling it around. So inflating and deflating these airbags, you can start rolling them around. And in the end, they open up, and in this module, for example, brings in a few rovers to start prepping the site. The first rover here is our digger. It's a very simple design. It has 4 wheels. You actually can't even steer them. It actually steers like a tank by just changing the speed of rotation of the wheels relative to each other. And it has a Victorian technology, which is a bucket wheel. It's a very simple way to scoop dirt. Because if you think of it, if you would use a digger, a normal digger that you would find on Earth, a digger normally works because it's a heavy machine. It has really reaction to actually kind of scoop up some regolith. You know, the gravity on Mars is 1/3 of the gravity on Earth, so it would just actually not be able to scoop the dirt up. So you have this really simple bucket wheel that scoops up the regolith, and then we have our little transporters, which are smaller robots that go underneath, pick up some regolith and start moving it about. So these are actually our site preparation robots. So now we have the habitat modules arriving, and they roll together again by inflating and deflating the airbags. They actually roll together, and they arrive in the same way. Activation of the airbags. I'm just going to go. Oh, we actually explained this already. There we go. So, but the habitats kind of deploy slightly differently. So what it is, there are dodecahedrons, and they open up, and inside they have 5 airlocks. That while the dodecahedrons open up, the airlocks move out, and in between the airlocks there's again an inflatable. So it's kind of like pops open. And then we have 3 connection pieces between those that just kind of lock themselves into each of the modules. Now, again, we need to build that big dome around it, right? Our protection shield. Now, as I already started explaining, we have different robots. We have, first of all, our digger robot that you see in the back here that digs up the regolith. The second one is our transporters, our RACTs. So they take the regolith and bring it to the structure, our building robots, which are these, the RAC-Ms. Now these are actually much smaller robots. They're about 20 centimeters. And what they do is for this process, we weren't bringing any material anymore, any binding material anymore to Mars. We're just going to melt them together. So we're using microwave technology. Each of these will microwave an area underneath them. Now this technology actually really already exists. There's a research group in Hawaii that is testing this with volcanic ash again, looking at can we actually kind of melt the regolith, the dirt together to build building blocks. And this is the technology that we're using now. So now, for the previous project on the moon, we didn't really look into the inside, what the inside really looked like. So we didn't really design it properly. So this time we thought, well, let's look at it. What would these spaces look like for the astronauts? Because we're going to have 4 astronauts there, living there for 500 days. Now, there aren't many precedents, but one really interesting precedent we found was the British Antarctic Survey. This is the South Pole base from Britain, and it's one of the largest ones out there. And it's an interesting analogy, because during the winter, anybody who's at that base cannot be evacuated. So you're there stuck for around 8 months. Right? There's no plane that can get there, there's no ship, there's no helicopter, there's nothing that will be able to get you out there. Right? It's actually easier to be evacuated from the International Space Station than it is from this base in winter. Right. It's an interesting design. It's got different modules as well. It stands on legs. And one of the reasons of that, I'm just going to show that really quickly, is that this is the an old base. This is Halley 3. The one I just showed before is Halley 6. And so previously they made these kind of very simple structures. The problem with them is that snow would actually kind of go on top of it and on top of it. And they wouldn't be able to dig it out anymore. And what happened is, after a few years, they just abandoned the base and they built a new one. Right? And what happens really is, while the base is kind of near the edge of the South Pole, it's kind of on a huge glacier. What happens after quite a few years, this is Halley 3. After many, many years, after a few decades, you find it, this is the edge of the glacier, basically, just, breaking off. So that's why nowadays it's on legs, and it actually can lift itself up. It lifts itself up onto the snow. So we thought it was an interesting design, but what we really wanted to know is how people live there. So we started to talk to the commander of the winterization team. So really lovely guy, John. We had him in for a couple of sessions, and we had long talks with him. Like, how do people live in such an environment? Because it's very similar to living on Mars and the Moon. You can't, for example, walk out. It takes you 20 minutes to get dressed to walk outside, and you have to be dressed in a very particular way. If you leave any skin open, that will really freeze immediately. So, interesting similarities. This is a kind of the main module is where their recreation module is, where they have their bar and their hangout area. And what they have there as well is a huge window. And actually enough, this is probably the most difficult part of this base, is that massive window on the South Pole. And this was something that we played with in the design as well. Do we have a big window? Do we want to have a big window in our Mars base? That would be a huge challenge, because the window is actually kind of an opening again to the outside. It won't be protected for radiation. So we played with that idea quite a bit. So this is some sections through the base. You see there's 3 modules interconnected. All the life support systems, so the generation of the oxygen and so forth, the recycling of water and so forth, always happens in the floor. So we have a floor system that can completely support each of the modules. We also looked at how much space do you want to have for yourself? How much space do you want to be communal space. And talking to John from the British Antarctic Survey, it was really interesting to see that he said, well, actually, yes, you want to have your private space, but that space can be really quite small. So we chose for actually quite a small berthing area, private berthing area. Let me just go a bit further here. So this is one of the models that we did. I spoke about that we have different connections. There's different locks, air locks. So some of them are used to then connect to another module, but other ones are slightly different. So we have some of them connect you to the other modules. Another one will connect to a rover directly. And different from our moon project is that we don't have an airlock anymore. The suit itself is the airlock. So if you want to do an EVA, space people love to use abbreviations, which EVA stands for extravehicular activity. So if you want to walk outside in a suit, basically, what you do, you climb in the suit from the back and you close the suit off and you go and start walking, you know. So there is no contamination of particles from the Mars base with the internal habitat unit, because that was a huge problem on the moon missions, that the regolith was really electrostatic and really abrasive. So you want to have a system that cannot bring anything inside. If you want to bring something inside, you can do controlled. Use the airlocks, you use a glove compartment. So this is when you would bring in some samples, so the astronaut could pick up samples and bring it into this sample area, this glove box area. So also you see I spoke about it has like three modules, each of them with 5 airlocks, and in between the 5 airlocks we have these inflatable modules. Well, within the inflatable modules there's an infill system, right? So we can have a toilet in there, we can have a shower in there, we have an office space in there. So each of them can be brought in separately. And we also kind of envisioned that these spaces would be filled in by the astronauts. So you would have, it's almost like an empty shell apartment, unfurnished. When the astronauts would come in, they would actually place these things in place. It also means that it's interchangeable. If one really fails, you can close that off and you can, you know, reorganize it if you want to. Yes, I thought it was going to crash, but it didn't. So we went a bit far. We went like, well, let's what would the astronauts look like? What would they be wearing? We actually even brought in a stylist to have a look at what would they be wearing, right? So there's a photo shoot even. Of course, the Cousteau reference is obvious here with the red hats, and started to look at what would the spaces be like. So a space might be a purely science area. So one of the modules would be a lab, which you can see here. But we wanted to then to have I was almost there. One thing you see like a massive screen and this kind of skylight. So each of the models have a skylight as well, because we thought it would be important to have daylight. Now, it was really impossible to, at the moon base, we still played with this idea of having some real skylights in there. We decided on the Mars base against it because we think technologically it would actually be too difficult to do, and we believe that screen technology in 20 years or in 15 years, when this hopefully would become reality, will be that good that we can just use screens to project maybe the outside environment or something from Earth. And this was actually also an inspiration that we got from the British Antarctic Survey, because John explained to us that one of the guys there who works in the garage area of the base, he actually uses a projector to project his local pub. You know, he likes to kind of feel that he's at home. So he just images from his local pub where he normally is and projects that. So we thought, well, maybe it does work. If technology is that good that you really feel that you're there, why not do that? And this is then the kind of final image of that Mars base being put together. Normally, you know, it would probably be fully printed before the astronauts would ever arrive. But you see the kind of the melters here are probably making a landing pad or some road here for the rover. I see them here finishing off the last layers of that dome structure. So I could talk for hours about this project, but I think I'm kind of way over time anyway. So let me finish here. Thank you.
So thank you very much, Javier, for sharing these pioneering research projects that you've been developing with the Foster & Partners Specialist Modelling Group. I'd like to say they're visionary, but you've kind of convinced me that they're also reality, and
they're totally reality. Yeah, no, they're not, yeah. We want to be the first architects in space, absolutely.
Okay, excellent. Yeah. So they're becoming reality?
Absolutely.
Okay, and with that, I'd like to invite any members of the audience who might have any questions for Javier to lift up their hand, so I can bring you a microphone. Where? There's one here. 1 second. Look.
How long does it actually take to 3D print them?
Well, we did a bit of an analysis on the moon base, and we think it would take about roughly 3 months. We were thinking we haven't actually done the calcs on the Mars base, but the great thing in space is that you have a lot of time. You know, that's one thing you have. So we're not too worried about that. Yeah. Okay. It's not like there's like showers of meteorites, right? There's probability that something might hit, and these are actually very small particles as well. So yeah, it's a statistic that something might happen to one of them. So, but the same thing happens in the International Space Station. I asked a question to one of the scientists at ESA once, and asked them, well, you know, we're protecting this whole Mars base, but what happened to the International Space Station? And he gave a very interesting answer. He said, well, you know, anything bigger than 10 centimeters, we can track that from Earth, and we'll just move the whole space station. Anything smaller than a centimeter, we can probably take the hit. And anything between, and then I was like, well, hang on, but what between the centimeter and the 10 centimeters? And like, oh yeah, that's probability. So yeah, so the movie Gravity could happen, maybe, you know. It's a risk. It's a calculated risk, these things. It's also, you know, we calculate the thickness of the shell. You know, it's again probability. You know, if a massive meteorite would hit it, yes, of course it would be destroyed. But you just look at what is the chance that that kind of size of meteorite would hit it in X amount of time. You know, you design buildings for the 100-year storm. You know, you can never design something for, you know, against everything. You know, it doesn't exist.
Talking about 3D printing, how does gravity affect the whole construction process, and what have you considered about the gravitation force in both the planets like the Moon and the Mars? How does it vary from the Earth?
Well, one thing that we were really a little bit worried about is, well, you still have gravity. 1/3 or 1/6, you know, there's still gravity. One thing that might be an issue is starting to scoop up regolith. So the way you do that, you might want to minimize the amount of dust that starts blowing around. So you know, especially on the Moon, that might be an issue, because there's also no resistance from the atmosphere. So if you throw something, it will actually really throw particles will start to move quite a long way. So it's a bit of a concern, but we haven't really you know, got into it that far that we kind of started testing that out, for example.
Hello.
Hi.
It's really nice to see everything is coming together, and as Matilda mentioned, it's not an idea, it's a reality right now. But I want to ask you about, like, when you get there, when you have a cheap flight, let's say tomorrow, and you arrive, how would you select where to build, where to start building? Because not in terms of environmental issues, but as like the property of owning a land, let's say. I don't know. So, and the other question is, like, the first one who gets there, will he be like owning the thing and start selling soil, regolith, whatever? How is it gonna work? Like, and because of all these things.
Who owns Mars?
Oh.
I think there are a few treaties out there, but I'm not an expert on this. But there are conflicting treaties as well. Like who owns what? I think nobody can really own it. I think that's the idea. But I don't really know what will happen if the what if a commercial entity comes or not.
International waters or something like that.
Yeah. Well, there's a great line in The Martian, I think, where where Matt Damon or whoever it is, kind of realizes that he's in international waters and that he's actually a pirate because he just entered a new spaceship at some point. So it's really weird what it really is. I'm not sure. And about was it which location it is? So for the NASA competition, we had to define a certain location as well. We chose the equators because the temperatures is a bit more. It's not that cold as on the poles, so that's one of the reasons why we chose it there. Yeah.
I was just wondering about freeze thaw action. If you have in the moon going from -100 to +100, and you're 3D printing the building, it's not really compacting the house or the building. How do you combat freeze thaw action where it's breaking down with the freezing?
Okay, say it again.
Freeze thaw action, as in on a mountain, if you have the rock on the mountain, it breaks down every winter.
Yeah.
And it turns into scree. I'm wondering, is there...
There are cracks happening.
Yeah, cracks.
Yeah. No, there is definitely concern. And we again is something, the moon project was a very quick project. This was a couple of months' work for us, and these were definitely concerns again. So what would happen, and these things that you want to test out and do lots of analysis on it, and you might want to print different structures slightly to kind of take it into consideration. What we did want to do is that it was totally under compression, so that would probably help. If you have cracks, if the system actually is under compression, you're probably much safer than working with a system that needs to be in tension at some point. So that's why they're actually quite dome-like structures as well.
Did you consider any other material other than regolith, in terms of the building? Like with the abundance of space junk around Earth for the moon project, maybe harvesting that in some form?
Not really, no, because it's like so easily available. It's just there, and it's mainly the only thing that is there. So it's kind of, in a way, it's probably the most environmental project we've ever done. Like using very local material. Yeah, I took that one out of the equation,
Xavier, thank you for...
No worries.
It's pretty amazing, actually, the presentation and both projects related with
sorry
Mars
about the hiccups and the technical...
Yeah. Okay, but I want to stay back in Earth.
Yeah,
so
let's come back.
The Mars is great and the Moon is great as well, but my question is whether from all this research that you have been developing, especially in collaboration with the European Space Agency and the NASA, and all the research that I am pretty sure that you have been developing for the material scale of the regolith or other similar materials that could be found there, I would like to ask, have you been learning something that could be applied back in Earth? Because at the end of the day, we do speak about building in extreme environments in terms of temperature or humidity and light, but also in terms of resources. Resources in terms of people working there, or let's say places that we really need to start thinking of machines that could be transported into a place, use the local material and construct on site. So do you feel that you have further knowledge that you can bring back to Earth?
Well, I think the whole idea of having much smaller machines, right? So definitely in the second project. In the first project, we still have like 2 or 3 printers going around. In the second project, on the Mars project, we're starting to work with a completely different idea. This is not one expensive machine. These are smaller robots that do very simple tasks that start to work more in a swarm behavior, because nobody sits there on Earth kind of controlling these things, really controlling them. They will have to have their own behavior. So that's something that we're really interested in. What would that be in construction? And you might even think, well, it might not be in construction, but it might be in excavation, in site preparation. There's already for example, Caterpillar is now already using mining trucks, these massive mining trucks. So they operate automatically. There's not one person, there's one person controlling 6 of these massive machines. So if you start thinking, well, if they kind of run these massive machines, why can't we start to use bigger or smaller machines on a construction site in that way? So we do think there is really scope for that. So that's one of the, we learned many things on it, but that's probably one of the things that we're interested to kind of apply further.
When do you see it happening?
Well, the interesting thing is when we started the Moon project, there was I think a timeline to have it by 2035, but then things happened, and then things got cancelled. So ESA wasn't going to go back to the Moon, but now there's a new director general at ESA, and he's very keen to go back to the Moon. So we hope there will be some more traction in it, and that we can do some more research on it, because this is just the beginning of it. And Mars, well, there's Elon Musk that wants to have 1 million people on Mars in 100 years, and he seems to be very, very serious about it. So who knows?
When do you think this technology will be applied on Earth?
In Earth? Oh, that could be quite soon. I think these things. It's just, what it is sometimes? It's really finding the right application for it. So there's a technology there, but what is the application? I think on Moon, for some reason, because the material is so expensive to get there, it made total sense. Right? For some bizarre reason, that was the most feasible way to do it.
I'd like to ask you a little bit more about because you were mentioning about the screen, about the future of...
Oh, yeah.
Yeah, and not specifically about that, but more about the evolution of the system, how you guys plan in a more computational and more evolutionary way. Why is it that you guys came out from this group of geometry, that just this type of shape will be the appropriate for this place, and not something more swarm, make from swarm intelligence type of technologies?
Are you talking about the printing robots?
I'm talking about the shape.
Of what?
The pentagonal shape that you guys are planning to...
Well, of the robots or of the module?
Both. I mean, because of the modules might have that shape. What is the reason? And why not that the shape of the robot will generate a different shape?
It probably could. It's not the robot shape is not really about if there's a pentagon shape or a round robot or something like that. It was a way to kind of tile the tiling pattern, and we felt that the pentagon kind of worked quite well. It's actually an overlap system as well, so it's not a perfect match each time. It's kind of that you kind of stamp it, and stamp next one. There's each time a little overlap, and the pentagon shape for the habitat modules, that worked out because how we start to connect them. If you put them quite close and you have connections, how many do you have? So we did quite a lot of studies in a way what these modules could be, and it's all about how many connections do you get between modules. And which modules gives you the most space as well. So there was a bit of design process, of course, happening in that. So why we chose that particular shape.
So, Xavier, thank you again, and maybe I can invite everyone to give a round of applause, a last round of applause to thank Xavier.
Thank you.
And thank you.